This is day one of graphing rational functions. And whenever we graph any function, it's important to first understand the characteristics of the parent function. So today we'll be working with f of x equals 1 over x, which is the parent function for rational functions. You can see that I already filled in the values for the table, and I did that by simply substituting my x values for x in the function. So when x is negative 10, the value of the function is 1 over negative 10. When x is negative 5, the value of the function is 1 over negative 5, and so on. I want to call special attention to the result when x equals 0. We have looked at two restrictions in class. One of those restrictions is that we cannot divide by 0. Well, in the parent function for rational functions, the denominator is x. So when x equals 0, we are dividing by 0, and the value of the function is undefined. I have written DNE here, which just means does not exist, and you can use that acronym whenever you want to indicate that the value is undefined or does not exist. If you were to plug this into a calculator, you would see an error at 0 because that's how the calculator indicates that the value of the function is undefined. Let's go ahead and take a look at the graph over here on the left. I've already plotted the points. These are just the points from the table. So I'm going to draw the function by starting on the left and connecting my dots. You'll see that we start near the x-axis and then we turn down and finish near the y-axis. Then the function on the right side of the y-axis comes down and then turns and finishes near the x-axis. With the basic shape of our parent function in place, we can take a look at these values. So the y-intercept. The y-intercept is the point at which the function crosses the y-axis. In this case, you can see that that does not occur. So the y-intercept does not exist. The x-intercept is the value, it's the point where the function crosses the x-axis. Again, we can see that does not exist. So DNE. Now let's identify our horizontal and vertical asymptotes. There's a reminder here of what an asymptote is. It's a line that a graph approaches as the value of a variable becomes extremely large or small. So looking at our horizontal asymptote first, that's going to be a line that moves left to right. We can see that as the values of x approach negative infinity and as the values of x approach infinity, the function is approaching a particular line. And that line is right here at y equals 0. So we'll put horizontal asymptote at y equals 0. Our vertical asymptote, as y approaches negative infinity and as y approaches infinity, you can see that the function approaches a line at x equals 0. Let me try that again. Here we go. So there's our vertical asymptote. Let's go ahead and write those as equations because they are a line. The horizontal asymptote is going to be y equals 0. And the vertical asymptote right here where x equals 0. So now we can find our domain and range. The domain is left to right. You can see that this goes to negative infinity and positive infinity. So it's going to be all real numbers. But we must take into account our domain restriction, which we can see visualized with that vertical asymptote. So x cannot equal 0. You can write this in interval notation if you prefer, which would be negative infinity to 0 or 0 to infinity. The range, also negative infinity to infinity, so all real numbers. But we have this same restriction, y cannot equal 0. So in interval notation, we've got negative infinity to 0 or 0 to infinity. I will be using set notation during this video, but again, you are welcome to use whichever one you are more comfortable with. So now we are going to look at transformations. The values used for our transformations will not be unfamiliar to you. We have our a, our h, and our k. So y equals a over x minus h plus k. So our a value is going to do a couple things for us. First, it impacts our vertical stretch or compression. So we'll have a stretch when the absolute value of a is greater than 1, and a compression when the absolute value of a is less than 1. The reason for the absolute value bars is that if a were negative 2, that would still be a stretch. The negative sign would cause a reflection. So we have a reflection if a is negative. So a negative 2 value of a would give us a vertical stretch by a factor of 2 and a reflection. I have not specified vertical or horizontal reflection, and that's because with our rational functions, a horizontal and vertical reflection both would look the same. So you can think about it whichever way is easiest for you. Our h value and our k value are exactly what you'd expect. H is the horizontal shift left or right, h units, and k is our vertical shift up or down, k units. Again, with h, you have to be careful here because the sign will be the opposite of what you expect because of this negative. So let's apply these transformations to the function on the right. Let's take a look at our a value first. A equals 1. That's this 1 here. So that will have no effect on our graph. Our horizontal shift, h, we have a positive 3 here. Notice that our equation is x minus h, so to get a positive 3, h must be negative 3. So h equals negative 3, which is a shift left 3 units. And then our k value is just this negative 5 over here, which means that we are shifting down 5 units. So I'm going to go ahead and put a point down to show this horizontal and vertical shift. We're going left 3, down 5. So put that point right there. What does this point mean? When we're dealing with rational functions, that shift is the intersection point for our horizontal and vertical asymptotes. So let's go ahead and put the horizontal asymptote there and the vertical asymptote here. And then the stretch or compression will determine the shape of the graph. So here we don't have a stretch or compression, so we'll have the same shape that we had with our parent function. So we can go over 1, up 1, put a point there. We can go over 1/2, up 2, over 2, up 1/2. You can keep going, plotting points if you'd like. Here on the other side, we'll have negative 1, negative 1, negative 2, negative 1/2, negative 1/2, negative 2. And then I'll go ahead and draw this function for us. There you go. So let's go ahead and fill out these values now. We've got our y-intercept. There actually is a y-intercept on this one. You can see the function crosses the y-axis right here. So how do we find the y-intercept? The key here is to remember that the x value is 0 at the y-axis. So if you plug in 0 for x and solve, you will get the value of your y. So if x is 0 here, we have 1/3 minus 5, and this is going to be written as a point. So our y-intercept is x is 0, y is negative 14 over 3. The x-intercept. We do have an x-intercept here. The function crosses the x-axis. So to find that, you have to remember that at the x-axis the value of y is 0, so we can replace y with 0 and solve for x. We end up finding that that is negative 14/5 and 0. The horizontal asymptote has shifted down 5. So our horizontal asymptote, and I'll go ahead and write this in green so you can associate it with the picture, y equals negative 5. And the vertical asymptote is going to be at x equals negative 3. Try that again, x equals negative 3. Okay, our domain is all real numbers. But where's the restriction in this case? X cannot be negative 3. And the range is also all real numbers, but our y cannot be negative 5. So now you're going to apply this to the next page. I want you to go ahead and attempt these on your own. I will explain them. So I'm going to take a moment to let you pause the video, try to solve all 3 of these, apply the knowledge that we just went over, and then I will explain them briefly. So go ahead and do that now. Alright, hopefully you've had a chance to complete these. So let's take a look at the answers. So for this first one, y equals negative 1 over x plus 2. Let's look at our a, h, and k values. A is a negative 1. Don't forget this negative goes with the a. So that simply means we have a reflection. Our h is 0 and our k is 2. So we're shifting up 2. So we shift up 2, place our asymptotes there. Our y-intercept does not exist because that asymptote is right on the axis. Our x-intercept, if we replace y with 0, gives us x equals 1/2. So 1/2, 0, you can see is the x-intercept. Horizontal asymptote is at y equals 2, and the vertical asymptote at x equals 0. The domain is all real numbers, but x cannot equal 0. The range is all real numbers, but y cannot equal 2. So our next one, f of x equals 8 over x. This looks very similar to our parent function, with the exception of the 8. So our a value is 8. That means we have a vertical stretch by a factor of 8. Our h and k are both 0. So you'll see that when we have a stretch and nothing else, these values all end up being the same as our parent function, because our asymptotes are right on the axes, the x and y axis. We've got no y-intercept, no x-intercept. Our horizontal asymptote is y equals 0, our vertical is at x equals 0, and our domain has these excluded values of x cannot be 0 and y cannot be 0. So what changed? The main thing that changed is the shape of the graph. Where we had on our parent function a point at 1, 1, we're now multiplying our y values by 8. They're being stretched by a factor of 8. So now we're going over 1 up 8 instead of over 1 up 1. Where in the parent function, if you go over 2, you'll be going up 1/2. We multiply that by 8, so now we're going over 2 and up 4. If we go over 4, we're up 2, and over 8, up 1. So you can see that this shape, if we compare it to the shape of this function over here, it's a much wider curve. It's not quite as tight as the parent function. So that's what our graph looks like, and that's what a stretch does. The last one here, Our a value is negative 8. Remember that negative goes with the a. So we have vertical stretch by 8 and a reflection. Our h value is negative 5, which means we are going left 5. And our k value is negative 6, which I failed to write. It's down 6. So there we go, down 6. So we go left 5, down 6, and that becomes the intersection point for our asymptotes. Our y-intercept, when x equals 0, if we plug that in here, we get negative 38 over 5. And our x-intercept, when y equals 0, plug that in here, we get negative 19 over 3, with y being 0. Our horizontal asymptote, y equals negative 6. Our vertical asymptote, x equals negative 5. And our domain restrictions, so all real numbers where x is not equal to 5, and our range is all real numbers where y is not equal to 6.